The Artemis II heat shield was bolted onto the Orion crew module in June of 2023. NASA identified the root cause of the Artemis I heat shield failure on December 5, 2024. 11 months after the crew hardware was already locked in place, that shield shed material at more than 100 locations during its first lunar speed re-entry in patterns that matched neither NASA's computer models nor the Arc jet tests from Langley Research Center. The agency's fix is not a redesigned shield. The fix is a different flight path. Orion was built to perform a skip re-entry, dip into the atmosphere, bounce back out, descend again. That maneuver has been eliminated. Artemis II launched on April 1, 2026, and is now carrying astronauts Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen toward the moon at approximately 25,000 miles per hour. The fastest crewed lunar return attempt since Apollo 10 hit 24,791 miles per hour in May of 1969. They are riding behind the same AV-coat material, the same block construction, the same manufacturing process that produced the failure. The only change is a steeper re-entry angle on the way home. The Artemis program spent $93 billion through 2025 and arrived at a point where flying around a known problem became the safest available option. What follows explains how a mandate to preserve shuttle-era contracts produced hardware that cannot be revised, a heat shield that cannot be replaced, and a trajectory workaround that exists because nothing else does. As of this recording, that workaround is being tested with 4 human beings aboard. Orion's heat shield uses a reformulated version of the ablative compound that protected Apollo astronauts returning from the moon between 1968 and 1972. Avco Corporation developed the original formulation starting in 1961, and NASA selected it for the Apollo Command Module in April of 1962. The material works by absorbing heat through controlled charring and gradual shedding, a process of deliberate destruction that keeps the spacecraft behind it intact. Production of the original AVCoat formulation ceased in the 1970s after environmental regulations restricted certain phenolic compounds in the mixture. When NASA chose AVCoat for the new Orion capsule in April of 2009, program manager John Cole acknowledged what the project faced: reviving the technology to manufacture material that performed the way Apollo-era AVCoat had decades earlier. The Artemis I heat shield used 186 pre-machined AVCoat blocks bonded onto a carbon fiber carrier skin, replacing the monolithic honeycomb design from Orion's 2014 Earth orbit test. Lockheed Martin chose the block approach because it shortened the manufacturing timeline by 2 months, not because it performed better. And that's where a second decision compounded the first. The Artemis II heat shield was made less permeable than the Artemis I version, specifically to enable ultrasonic quality control testing of the bond between AVCoat blocks and the carbon fiber skin. The modification that improved testability increased the shield's susceptibility to the exact failure mode under investigation. Nobody had flown a segmented block format heat shield at lunar return speeds before Artemis I. Nobody had flown one on a spacecraft this heavy either, since Orion's crew module weighs roughly 50% more than the Apollo command module. The combination of larger shield diameter, block segmentation, reformulated AVCoat, and higher vehicle mass had never been validated together. NASA's pre-flight ground testing used higher heating rates than Orion actually experienced during re-entry. Engineers assumed problems would appear at higher heat loads. The actual flight produced lower heating during the skip maneuver's dwell phase, the period when Orion lifted back out of the atmosphere before final descent, and that lower heating allowed gases to accumulate inside the AVCoat faster than the porous char layer could vent them. The failure mode appeared at less severe conditions, not more severe ones. The test envelope never included the scenario that caused the problem. The NASA Office of Inspector General's May 2024 audit identified 3 anomalies potentially endangering crew. First, the heat shield spallation. Second, power distribution irregularities. Third, the separation bolts. 3 of the 4 separation bolts embedded in the Artemis I heat shield experienced unexpected melting and erosion through their thermal barriers during re-entry. The OIG's documented concern was specific. Bolt melt beyond the thermal barrier could expose the vehicle to hot gas ingestion behind the heat shield, potentially exceeding Orion's structural limits. The OIG released photographs of the Artemis I heat shield damage on May 1, 2024. Before those images became public, official NASA language described char loss, controlled and clinical. The photographs showed something different. Not gradual erosion, gouges, block-shaped voids where chunks of avcoat had simply departed. The 2008 Manufacturing Development Unit was the first full-scale avcoat heat shield anyone had attempted since the early 1970s. Between 35 and 40 years separate the last Apollo-era avcoat production run from the Orion restart effort, a gap long enough for the people who knew how to build the original material to retire and for the institutional memory of how it was manufactured to degrade beyond recovery. This pattern is not unique to avcoat. After Apollo ended, what NASA knew about building the F-1 rocket engine degraded to the point where the agency had to reverse engineer its own hardware. In 2012, engineers at Marshall Space Flight Center disassembled engine F6049, a flight-ready unit swapped out of the cancelled Apollo 19 mission, and spent 4 months 3D scanning more than 400 components. Original design documents produced under deadline pressure without computerized aids told only part of the story. Each F-1 had been hand-built with manufacturing quirks that nobody recorded. Rocketdyne's 1990s retention program captured some institutional knowledge through tape-recorded interviews with original designers, producing 20 volumes of material. Even with that effort, a 1992 estimate placed the cost of reactivating F-1 production at $315 million in 1991 dollars, with $100 million allocated for test engines alone, for an engine that had last flown in 1973, 19 years earlier. The cost of forgetting how to build something is never zero. It compounds. The avcoat reformulation faced the same compounding. The Constellation program, which preceded Artemis, was cancelled in 2010 after somewhere between $9 and $12 billion in development spending. When Constellation ended, engineers who had worked on the 2008 Manufacturing Development Unit dispersed. Some retired, others moved to different projects, and the procedural memory required to manufacture avcoat to Apollo-era performance standards scattered with them. What the Artemis program inherited was not a production capability, it was an attempt to reconstruct one. Former NASA Deputy Administrator Pam Melroy described the earlier Orion test shield as very finicky and acknowledged it would be difficult to reproduce quickly. Lockheed Martin switched to blocks for producibility. But the honeycomb design, while impractical for serial production, may have contained crack propagation in ways the block format does not. The 2014 test flight showed cracks in seams between honeycomb sections, but those cracks stayed contained within the titanium honeycomb structure. Avcoat blocks have no such natural barriers. The NASA Authorization Act of 2010 directed the agency to develop a new heavy-lift launch vehicle by utilizing existing contracts, workforce, industrial base, and capabilities from the Space Shuttle and the cancelled Constellation program. Section 302 set a target. The Space Launch System was supposed to be fully operational by December 31, 2016. None of that language was accidental. Senators representing states with shuttle-era aerospace employment, Alabama, Florida, Texas, Utah, wrote requirements that would preserve jobs and contractor relationships regardless of whether the resulting hardware was optimal for the mission. The RS-25 engines powering the SLS core stage trace their lineage to the 1960s, with formal development beginning in 1970. 16 heritage RS-25 engines remained after shuttle retirement, upgraded with new engine controllers for SLS, but otherwise the same power plants that flew on the orbiter. Unlike the shuttle program, where each RS-25 was reused across multiple flights, SLS discards its engines after every launch. They fall into the ocean with the core stage. The solid rocket boosters use steel casing segments left over from shuttle inventory. Aerojet Rocketdyne received $3.5 billion to restart RS-25 production and build 24 new engines. The per-unit cost, averaged across that contract, exceeds $145 million, though this figure includes substantial non-recurring costs for reactivating a production line that had been dormant. Every attempt to cancel or scale back SLS has been overridden by Congress. The Obama administration proposed ending SLS in 2014 in favor of commercial alternatives. The Senate restored funding. The first Trump administration's fiscal year 2020 budget dropped funding for advanced SLS variants. Congress restored it. The second Trump administration's fiscal year 2026 budget proposed ending SLS and Orion after 3 flights, describing the rocket as grossly expensive and 140% over budget. Congress overrode that proposal through the One Big Beautiful Bill, with Senator Ted Cruz's amendment allocating $4.1 billion for SLS rockets through fiscal year 2029. The available inventory of shuttle-era solid rocket booster casing segments limits SLS to approximately 8 flights total, regardless of what commercial systems emerge, regardless of what any administration proposes. The trap is mechanical as much as political. The hardware NASA was mandated to use is running out. 3 advantages drove the original skip re-entry design for Orion. Extended landing range was the first. Orion could fly up to 5,524 miles beyond the atmospheric entry point compared to 1,725 miles for Apollo's direct approach. Heat distribution was the second because splitting deceleration into 2 atmospheric passes reduced peak heating at each event. Reduced G-forces was the third. NASA's own design rationale documented the trade-off. The skip re-entry was designed to produce approximately 4 Gs during each of 2 separated pulses, rather than a single sustained spike. Direct re-entry eliminates all 3 of those advantages. The Artemis II crew will experience higher G-forces in a single continuous event at approximately 25,000 miles per hour when they return from lunar distance. Landing zones will be more constrained. The AVCOAT heat shield will absorb its thermal load in one continuous exposure rather than 2 separated passes. NASA's Flight Readiness Review concluded on March 12, 2026, with a unanimous go decision. Agency leadership characterized the risk profile as acceptable, noting that the trajectory adjustment had restored margin to the heat shield's thermal limits. NASA Administrator Jared Isaacman, who took office in December of 2025, has prioritized an accelerated mission cadence under his ignition agenda, with a firm target of landing astronauts on the Moon by 2028. The actual fix for the gas-trapping failure mode, a modified AVCOAT formulation with improved permeability, is currently being applied to the Artemis III heat shield. That shield was not ready in time for Artemis II. In February of 2026, NASA officially redesigned Artemis III as an Earth orbit docking test with commercial lunar landers, similar to what Apollo 9 accomplished in 1969. The first crewed lunar landing is now targeted for Artemis IV in 2028. The reformulated AVCOAT will fly for the first time on Artemis III, which remains a crewed mission. No uncrewed test is planned for the new formulation before it carries astronauts. Charles Kamada flew the return-to-flight mission after Columbia and later served as Director of Engineering at Johnson Space Center. In January of 2026, Kamada appeared on 60 Minutes and stated publicly that he did not believe Artemis II was ready to fly safely. Kamada's documented concerns drew explicit comparisons to the organizational patterns that preceded the loss of Challenger in 1986 and Columbia in 2003. Schedule pressure overriding safety culture. Models substituted for empirical testing, dissenting engineering voices dismissed. He called it Go Fever. The Artemis program has spent over $100 billion across its development phases. The first crewed lunar landing, originally targeted for late 2024, has slipped to Artemis IV in early 2028, a 4-year delay from the initial announcement. Artemis III, which was supposed to be the landing mission, has been redesigned as an orbital systems test. The heritage mandate that shaped Artemis, the congressional requirement to preserve shuttle-era contracts and capabilities, produced a rocket that costs approximately $4.2 billion per launch and a heat shield that cannot be replaced without years of additional delay. That same mandate, the one that sustained the program through 3 presidential administrations, also locked it into hardware decisions that cannot be revisited without starting over. The timeline that opened this video, a heat shield installed 11 months before the failure of its predecessor was understood, is not an accident. It is the consequence of a program structure where hardware must be committed before knowledge is complete, because the schedule cannot wait for the learning. The Government Accountability Office reported in September of 2023 that senior NASA officials acknowledged the SLS program is unaffordable at current cost levels. The same report documented something else. NASA does not plan to measure production costs to monitor that affordability. The program structure that produced a trajectory workaround as the only available response to a materials failure is the same structure that, as of that 2023 report, does not measure its own costs. 4 astronauts are currently in transit to the Moon behind a heat shield, flying a trajectory designed to avoid a failure mode rather than fix it. The corrected shield is still being built. Whether the workaround holds is a question that will be answered in the coming days.